Let's go to the Wikipedia page for an inductor and have a look at what we can see. We get the basic equation for the definition of an inductor here. The inductance is equal to the magnetic flux linkage generated by a given current. That's this equation here we are seeing, and it goes on to provide some descriptions about the basic concept of the inductor, and then we come over here to the constitutive equation, which is probably what we are familiar with when defining what we would consider as the most basic equation of how an inductor behaves. And here what we can see is that we get a voltage and current relationship related to the inductor value. And we know that an inductor typically tries to maintain the current flowing through it at the absence, or rather when the current source is disconnected to it as well. And as a result, we can see that the voltage at the upstream end of the inductor reaching really high values. That's what we can see in practice, and this equation is what specifies that. So perhaps what we can do is we can try and simulate this behavior on Spice and just see what we get. So let's go over to Spice and open a new schematic, and let's start with an inductor because that's what we are concerned about here. And let's now add a resistor. That's the load resistor. And I will also add a resistor on the upstream end, just in case I need to use it. And what we need is a voltage source as well. So let's add a voltage source here. So what I will do now is add a voltage control switch as well, so that I will have better control of the switch on and off functionality of the circuit. Okay. And let me join this now. And also, this is not the only way, obviously, to simulate this. This is just something I'm doing right now. This may work, may not work, and I'm sure there are better ways to do the simulation. This is obviously just one of many ways. I hope. Okay, and let's just give this value of 1 Henry. Let's make it almost an ideal inductor. Okay, and then let's make this 100 ohms. And for the time being, I don't actually want any resistor that might actually have any effect here. So I'll just set a arbitrarily really high number. Okay, and then let's say I'm trying to give 10 volts from this voltage source. So I will need this switch to really turn on when I reach 10 volts or close to 10 volts, and then turn off as soon as it starts dropping. Okay, so let's add a directive to just have that functionality working. So creating a model called mySwitch, and the turn on voltage, let's say it's 9, and give it a hysteresis value of 0.5, let's say. So as soon as it falls to 8.5, the switch will turn off, and then when the switch is on, I want it to be a really small resistance, and when the switch is off, I want it to be a really high resistance. Okay, so I think that looks okay. Let's see what will happen. All right, that's the model, and then I will type that name here. My switch. All right, and now what I want to do is I want to give a pulse, rectangular waveform from this voltage source, so I can actually observe those edges where the supply turns off. Really, um, that's where I will hopefully see that spike, um, which we are trying to simulate. All right, so I need a pulse here. Uh, so let's do a pulse. Initial voltage is 0, voltage on 10. Let's give it a start delay. Rise time, I don't really want anything, but I think it's best to have a very small value. And then let's say we want it to be on for 1 second. So we have a delay of 1 second, on for 1 second, that's 6 seconds. Then probably turn it on off for another couple of seconds. So maybe total period is 8, and let's just have this running for 1 cycle. Okay, and that's that. Yeah. Uh, can I move this? Yeah. Okay, let's just move it there. And then we want to simulate this for 8, let's say 11 seconds, and we want to see the startup conditions as well. Okay, I think that's probably good enough to just see what happens. Maybe we can name some of these nets. Okay, probably not needed, but I guess we'll see what happens. Okay, maybe let's just see whether this is going to run. Okay, yep, my switch. Firstly, I need to give a ground here. Can't find the definition. Oh, I think I forgot some syntax here. I need to use that term there. Okay, yep, that seemed to work. Alright, so let's first see what we are getting at the voltage source. We can see our pulse. Alright, let's maybe add another plot, and let's observe the current here. Okay, so we see that the current sort of follows that path, and next maybe let's add another plot pane, and let's try and observe the voltage at this point. Okay, so here we are seeing that spike, right? See, it's gone to negative 4.4 megawatts. Probably not realistic in a practical sense. We wouldn't see such high voltage, but we are seeing a spike, and we are seeing a negative spike, and I think that's what this equation has as well, right? So let's try and zoom in here a little bit. Okay, so here we can see that a bit better once we zoom in. So we see that the voltage from the supply is dropping, and then that's the current through the inductor. Yeah, we let the current from the voltage source into here as well. Okay, let's add the current from here. All right, so yeah, but the light blue is the current coming from the voltage source, and the dark blue is the current through the inductor. As you can see, uh, the current continues to flow past the inductor even when there is no current being provided from the source, and that's the energy stored in the inductor being pushed out to the load, and and that is done by the voltage on the upstream point of the inductor going to an extreme and basically trying to keep that current flowing through the inductor until it can no longer sustain that. Okay, so that's what we are seeing, and as per the equation, as well as that's what we are supposed to see. Okay, and what will happen if we change some of these values? If I change the inductor value, the inductance, I'm expecting to see a higher peak voltage, I'd imagine. So let's just see what we get. Okay, and as you can see, I think we just did see the peak voltage increase quite a bit here. So I think earlier it was about 4.4. Now it's probably reaching 5 megawatts as we change the inductance from 1 Henry to 2 Henry. Okay, and typically what we do to solve this issue is we add a diode, right? So let's insert a diode and see whether this peak will disappear. So we typically add a diode across the inductor in such manner. Okay, diode. Maybe let's just pick something. Okay, I will just pick this diode. And now let's run this again. Okay, and see now we don't actually see those peaks here. Okay, so that's that voltage at this node. Earlier we saw it going to negative 5 megawatts. Now it's not doing that. You can see it's going down a little bit, but obviously that's negligible. Yep. So that equation essentially shows how the inductor wants to keep the current flowing, and the voltage across the inductor is equal to the inductor times the rate of change of current. And I think we've seen that by this simple simulation. As I said, this is probably just one way. Maybe this is not the ideal way, but I think we saw something of a spike there, which resembles what we see in practice. So I think that's achieved what we wanted to see here. Okay, so now we looked at the transient situation of the inductor when the power is turned off. Next, perhaps let's look at how the inductor behaved in a steady state condition, specifically when sinusoidal currents pass through it. And I believe that there are some equations on this page that defines that. Let's scroll down. Okay, I think this is that section. So we are looking at the circuit analysis. So we are looking at that same equation, which is the relationship between the time varying voltage across an inductor with inductance L and the time varying current passing through it. Okay, so if we replace IT with a sinusoidal current, we can see that the voltage is described as such. And what that shows is that the current lags the voltage by 90 degrees. So let's try and simulate that on Spice. Perhaps we can modify this circuit to achieve what we want. Okay, maybe let's first delete this diode. Okay, and maybe I will turn this into a series resistor. Okay, and now rather than giving a pulse, I will be giving a sinusoidal voltage. Okay, do I need the voltage control switch? Can probably leave it, but I don't want it turning on and off as the sine voltage obviously behaves as it does. So I might need to create a rectifier here. So let me start by maybe creating a bridge rectifier. There are again many ways to achieve this. I'm just doing it in one specific way. Let's just choose a diode. 20 amps. Yep, let's go with this one. Okay. Uh, and let's do that. Yep, I think that should be good enough. And we need to connect the negative side to here, and let's connect the positive to there, and I need to disconnect this. Okay, so let's now connect the rectified output to the switch. Okay, I also need to add a capacitor to get rid of the rectified output and rather make it a smooth DC waveform. So let's set a capacitor. Okay, let's do something. Let me just do that. Or rather, I might just rotate it. Mm, yeah, alright, let's try that. Might also want to add a resistor to discharge it when I turn it off. Okay, so let's now connect that as such, and let's connect the negative sides together and join it as such. Okay, let's give this a value, and let's make this 100 micro. All right. I think that looks okay. So we've got the bridge rectifier here, and then we got the negative going here, and then the positive, and taking the rectified output and adding some capacitance to smoothen the waveform. Okay, we need to change this. Okay, we'll put this back to 1 Henry, which was our initial value that we were testing. Okay, since we made this one, let's just make this one as well. And now I need to change this from a pulse to a 50 Hertz sinusoidal waveform. So let me do that. DC offset 0. Amplitude we will keep at 10. Let's change the frequency to 50 Hertz. Okay. 0 degrees, starting at 0 degrees, I suppose. We'll keep this time delay values. Let's leave them as such. Cycles, let's just do 100 cycles. Okay. And now the switch, I don't want to wait till it goes all the way to the top to turn it on. I want to turn it on at I guess a low value. Maybe I guess let's just say 1.5. And when it's on, I want it to be having a very low resistance, and when it's off, a very high resistance. So I think that's okay. Don't want to simulate it for 11 seconds. Let's maybe simulate it for 2 seconds. Let's just say maybe we might want to reduce it. I don't know. Let's see what we get. Okay. Then that looks okay. Let's run this and see whether we get any errors. Well, it seems to work. Do we need what we are seeing here? I don't know. Maybe let's just delete these. And let me first check to see whether this is getting a DC voltage. I would like to see this being more of a flat voltage waveform. Why am I seeing this? So it's definitely rectified from the looks of it. Do I need to increase the capacitance here? Uh, okay, maybe because I'm looking at this with respect to ground. So perhaps what I'm looking at is not really correct. I think I want to be looking at that. Okay, looks like we are getting somewhere. Maybe, yep. Now, anyway, my turn on is at 1.5, so it'll turn on here and then it'll keep running and turn off. So I don't actually mind having a bit of um, as long as it's above 1.5, my switch will stay on, so I don't mind having this over here. So I guess I'm happy to leave it as such. All right, and then I don't necessarily need to see this. Maybe we will just add another plot and then we'll just look at the voltage seen at the supply and around here. Okay, so we can see that on either side of the switch, the voltage seen is same. It seems to turn on at almost the same time and turn off at the relevant time. So I think that's good enough, right? So we can don't necessarily need these, or maybe I do, but let's just delete these and then. All right, so what are we looking at? So we are trying to observe the voltage and the current across the inductor, I suppose, and see whether we are observing that 90-degree phase shift. So on one graph, let me just plot the voltage waveform just upstream of the inductor. Perhaps on the same plot, I'll place the current waveform as well. Okay, and I think we are seeing something. Let me just delete this pane and let's just hang on. Let's try and let's run this again. I don't know what I did. Okay, let me just zoom in. Okay, so yeah, we do see that 90-degree phase shift. As you can see, that's the peak value of the voltage waveform. So if the current waveform was in phase, the peak of the current will be directly under the peak of the voltage. But it is fairly clear that the current waveform has shifted by 90 degrees. So, over here that's 0, 90, 180, 270, 360. It's the typical sine waveform. So 0, 90, 270. So, oh, sorry, 0, 90, 180. So the peak of the voltage is at 90, whereas the peak of the current waveform sits around the 180 mark. So that's the demonstration that the current waveform is lagging the voltage waveform by 90 degrees uh, based on what's shown here. What's shown here. Okay, so looking at the voltage at the resistor and then the voltage here. Okay, we are seeing quite a drop. I suppose that's because the voltage across the resistor is quite small. Maybe let's just increase this value and see whether we get something more significant. So looking at the voltage waveform before and after the inductor, we do see some difference in the phase. Basically, at this point of the resistor on the load resistor, by the time the current reaches the load resistor, the current waveform has undergone that phase difference. So when you look at the voltage at the load resistor, the voltage phase will take the same phase as the current across it. And therefore, we are seeing that phase shift when we look at the voltage at two different points on this circuit, one upstream of the inductor and then the second downstream of the inductor, which is the voltage across the resistive load. So I believe that makes sense. That is expected because if we look at the current waveform across the resistor, you will see that the current waveform is in phase with the voltage waveform across it as expected. So what that means is obviously the voltage waveform across the resistor will have a phase difference compared to the voltage waveform when we look at it upstream of the inductor. So that seems to make sense to me. And so that's what we simulated on this SPICE simulation. The fact that the current lags the voltage by 90 degrees. Coming back to this web page, which describes the inductor. So we've looked at the behavior during a sinusoidal waveform. Looking at the bottom here, we also see another equation of an exponential decay. So if an inductor is connected to a direct current source with a value I where our resistance R, and then the current source is short-circuited, the differential relationship above shows that the current through the inductor will discharge with an exponential decay. So this is a fairly common equation that we see alongside inductor behavior. So let's perhaps simulate this one and see what we observe. Okay, so what it says is we need to short circuit this current source at some point. Um, and again, it will be a DC current source. So I will have to change this to a sinusoid. All right, let's see whether I can move some of this stuff just a little bit to the side here, because I want to add another switch which can generate a short circuit through it when I want to, right? So this one says that I need to short circuit the current source. So let's try and do that. So let's now add a switch. Perhaps I can just copy this switch and rotate it. Let's try and get the orientation right. Okay. And I need to control the turn on and off of it. I can use the same signal that controls this switch. Take the positive from here and connect it to the positive, and connect the negative to the negative of the existing switch. But if this switch operates at the same time as this, it's simply going to create a short circuit loop here. So effectively, I need to invert the function of switch 2 compared to switch 1. So as soon as switch 1 turns off, I want switch 1 to turn on, and vice versa. Right? So I might just be able to copy this model and let's call it my switch 2, and essentially I just want to invert it. So when I rather have it turned on, I want it to have a really high resistance. I mean, let's just add another 0 here. And then when it's off, I'm just short circuiting it. So I've just swapped the resistor values when it's on and off. So it essentially turns on and off theoretically same as S1, but what it means when it's on and off is just inverted. Okay, and then let's change this to my switch 2. All right. I think maybe let's just drop the resistor values of these ones a bit to start with. We may need to change it again later on, but let's see what we get. All right, and then I need to change this one from a sinusoid to a pulse again, basically a DC source. So we keep the voltage at 10. We will just give it a bit of a time delay to start. Okay, I don't really want any gradient during the turn on and turn off, but let's see. Let's just make these really small values, and then I want the on time to be a certain amount. Let's keep it on for 0.1 here, so make it 2 in total. And then I want to see mostly what happens when it turns off. So I want probably to have about 1 second after it turns off. So in total, let's make it 3. And then let's just observe it for a single cycle. Okay, so I've got 3 seconds there. So this needs to be a minimum of 3. Um, let's just run this for 4 seconds. Okay, do I need to change these on and off values? Don't think so. Um, yeah, let's just leave it at that and see what we get. Okay, let's run this. Alright, I seem to be getting the sort of thing I'm expecting right on these existing graphs without even changing anything, which is positive. But what am I looking at? Let's just delete this and maybe start again. Okay, so let's look at the voltage here first, the source voltage. Yeah, that's our pulse. So what happens is as this turn off, this is going to short circuit, right? So let's look at the voltage here. So the voltage is the same. Okay, and let's look at the current through here. That's what we are concerned about. So what we can see is when in this turns on, there is a exponentially rising curve here. I think this equation captures the turn on exponential as well as the off exponential as well. Okay, so doesn't quite reach the top bar because it's current, so yeah, it might not need to necessarily reach the top of the voltage curve. So looks like it's reached that equilibrium state, and then once you turn off, you still get some current flowing. So where is this current coming from? So let's just look at the, maybe let's at the current waveform that's provided from the source itself. Okay, see, that's that light blue one. So as you can see, when the source is turned off, the current from the source essentially drops to 0, yet there's some current flowing through that inductor. So that's the energy stored in the inductor in the form of magnetic flux that's being continued to dissipate through this closed loop circuit now, through the switch that has been short circuited until the inductors dissipated all its energy. And that waveform of that energy dissipation takes the form of an exponential decay. So that's what we are seeing here. And that's a function of the decay is a function of the resistance and the inductance. Okay. And if you change the resistor value, the total steady state current through the circuit is going to be lower anyway for a given voltage. So the time taken for that current to dissipate may not necessarily be longer because the steady state current in itself is lower. Uh, So maybe let's just double this and see what we get. So here by about 2.8 seconds, the current reaches a value close to 0 with 5 ohms. And now as I increase the current, it reaches that similar value at about 2.4 seconds. So the decay curve is a bit steeper as the resistor value increases. But what you should note is that the maximum current value here is now just about 1 amp. What was it when it was 5 ohms? I would imagine it's double. Yep, so that's closer to the 2 amp mark. So that's why you see, because the steady state current is half, when you increase the resistance, the current decays to 0 quicker, right? So what happens if we double the inductance here? So at the moment it decays to 0 at about 2.4 seconds. The current is close to 1. Okay, as the inductance increases, you can see now the behavior of that curve. It's obviously the waveform is exponential decay, but the decay is uh, degrading at a lower rate, so the current takes 2.8 seconds to sort of reach that value that's close to 0 uh, when we increase the inductance here. So that's the behavior we observed with this SPICE simulation that's defined through this exponential decay curve for the current through an inductor when there's a resistance in the circuit. We can also have a look at this exponential behavior on MATLAB. We can plot some curves, and I have experimented with this a bit earlier. So let's just jump onto MATLAB and have a look. Okay. So here we are just looking at an exponential curve e to the power of minus 2t. Okay, so that's what we get. That's exponential decay. And similarly, we are looking at the exponential rise here of that same one. So these are the initial conditions, or rather the maximum values. So how can we get these maximum values compared to this one? So if we just look at the total resistance, in this case we can take the total resistance as 10 and the total, or the DC voltage is 10. So that means the total current, obviously with Ohm's law, is going to be 1 amp, right? So maybe let's just write that here. Okay, so maybe I will just write that, and I'd expect to get a similar waveform. So I have added these ones here. Okay, and then let's rerun this. Okay, I think I need to put the multiplication sign. Yep, so maybe I should just change the
title. Alright, so yeah, it's basically taking that same form. So that maximum current value is defined by the resistance on that circuit in this case. So that's what we are seeing here. And okay, I've done that here already. And that's essentially that same waveform. Okay, and here I just got a fixed value, but here I've actually plugged in the resistor and the inductor into this equation. Similar to that equation we saw here on this web page. So what we actually want to observe is how this curve behaves with changing values of inductors and resistors, I suppose. So what we can potentially show is, what I have actually done here is use that same equation and I changed the resistor values. And with changing resistor values of the circuit, the load resistor values, obviously as the resistor values increase, we can see the total steady state current decreasing. We are interested more in this exponential curve, as we see as the current changes, the time it takes to reach that steady state value increases as well. Okay, and then we're looking at the exponential decay side of things. Again, I plotted plotted the graph to show 4 different resistor values. So as you can see, as the resistor value drops, the time taken to reach that zero current value is increased slightly. Okay, that's what we see here. Maybe we can set the resistor value to a common figure. Okay, in this case, let me just indent this and keep this at 100. And perhaps increase this one. And see what we get. Okay, we are now changing the inductor value while keeping the resistor value at 100. Let's see whether this will work. All right, I need to change some things here. Yep. Uh, okay. I need to get the case correct. Yep. All right. Now it looks like it's working. So in this case, what I've done is I've now changed the resistor value to be a constant 100, and I'm increasing the inductor values. Right. So now we can see that I probably should change that. Uh, okay, so that looks a bit better. Um, yep, so as the inductor value increases, you can see that the waveform of the exponential decay gradient becomes a low value, so it takes longer to decay. Perhaps I need to increase the time axis to be a bit more, or rather, I need to change this one. Yeah, yeah, that looks better. And yeah, that shows what we saw on the simulation as well. So as the inductor value increases, the exponential decay takes longer for the current value to reach 0.